اوكي السلام عليكم كيف حالكم uh, we are starting a new chapter, oxidation and reduction. This material is not in your textbook. Even if there is something similar, do not pay attention. The only material you required for this chapter is what I give you. I will also place the PDF of the slides also on e-learning for you. So this is very important type of reactions in the soil system and the environment surrounding the soil, as we will talk about it as we go on. The hydrogen ion and the electron have been called the two master variables that govern chemistry. What we mean by the master variables, that means the two most important, the two major variables that govern chemistry: hydrogen ion and the electron. The availability of hydrogen ion and electron alone and together often determines the direction, rate, and end products of organic and inorganic reactions. This is very important. This is why they call them the two master variables that govern chemistry. The availability of hydrogen ion and electron, each one of them alone or together, often determines the direction, which way the reaction will go, to the right or to the left as we write it, the rate, how fast that reaction will go, and the end products. What do we get out of this reaction of both organic and inorganic reactions? Oxidation, you have learned it in chemistry, is the loss of electrons by a substance. And reduction is the gain of electrons. So when we say something is oxidized, that means it lost electrons, or the oxidation state increased also. It's said that way. And the reduction, of course, is the opposite, is the gain of electrons. Oxidation and reduction always occur together because a substance can only donate electrons if another substance can accept them, and vice versa the other way. So, of course, you cannot have oxidation without reduction or reduction without oxidation, because we talk about loss and gain of electrons. You don't lose an electron unless another substance is going to gain it or accept it. Many inorganic soil chemical reactions and virtually all biological reactions of carbon, nitrogen, and sulfur are oxidation reduction. And many times, in most cases, in many textbooks, you will see the abbreviation redox. It comes from reduction, oxidation. So they abbreviate it as redox reactions. So many inorganic soil chemical reactions, and virtually all, when we say virtually, that means almost all biological reactions in the soil are oxidation reduction or redox reactions. We will see examples as we go on. Most redox reactions also transfer hydrogen ions. So not only remember loss and gain of electrons, but they also transfer hydrogen ions. The significance of hydrogen ions versus electrons in soil chemical reaction depends largely on the presence or absence of oxygen. So, which one is more important? Is it the hydrogen or the electrons in the soil reactions that take place? That is determined by, do we have oxygen? Do we have aeration? Will a good supply of oxygen or lack of oxygen in the soil system? And you remember, lack of or the absence of oxygen, that means you have too much moisture in the soil. That will reduce the aeration, and of course, it will reduce the oxygen. Oxygen is the major electron acceptor. That is the major oxidizing agent in nature. That's probably where oxidation came from, because oxygen is the major oxidizing agent in nature. Remember, oxygen, the one we are talking about, is O2, the oxygen that you breathe, the oxygen that's available in the environment is O2 with zero valence. It's the gas, it's the oxygen gas. It is the major electron acceptor. When it has a zero valence, O2 with a zero valence, if it accepts electrons, then it becomes negative. It enters into reaction and becomes part of compounds, of all types of compounds. The availability of electron is rather fixed in aerobic soils. Aerobic, when you have the availability of oxygen. Aeration is good, that means availability of oxygen. So the availability of electron is rather fixed in aerobic soils where oxygen is present. That's why we said aerobic means the presence of oxygen, because aeration is good. The presence of the soil air is good, and of course that has oxygen. So electron appears to be insignificant compared to the importance of hydrogen. Go again. The availability of electron is rather fixed in aerobic soils. It's there in known amount, it's fixed. Where oxygen is present, so the electron appears to be insignificant. In this case, it's not that important compared to the importance of hydrogen. Remember, at the beginning, we told about the importance of hydrogen and electron being the two important factors in the chemical reactions that take place in soil. So if you have oxygen, if you have aerobic conditions, then the electron is insignificant, it's not important. Anaerobic conditions, if we have anaerobic conditions, which means there is lack of oxygen, when there is no well aeration, not good aeration conditions, then you have lack of oxygen. The conditions will be anaerobic conditions. That means the absence of oxygen. Under these conditions, slow the rates of root metabolism and ion uptake. Remember, oxygen is extremely important for the respiration of the plant, and respiration of plants takes place through the roots, not through the leaves, not through the upper part, as some people might think. Of course, you're agriculture students, so you should know that. So the metabolism starts where the oxygen is taken by the roots, okay? So if there is a lack of oxygen, there is slow rates of root metabolism and ion uptake from the soil solution. All this talks about aerobic conditions. All of these are anaerobic conditions. They slow the rates, they weaken the anaerobic conditions. All of these statements belong to this. Weaken root resistance to soil pathogens. That means the roots can be attacked easily by pathogens that are in the soil, and so the plants getting pathogens and get problems of weakness. Increase the concentration of undesirable reduced ions in the soil solution. We'll talk about also some of this later. So the concentration of undesirable reduced ions, because of lack of oxygen, we don't have the oxidized forms of the ions, we have the reduced forms of the ions. And so when they increase in concentration, these reduced ions, these are not good for the plant. Carbon dioxide is formed when oxygen accepts electrons from plants and microorganisms. Carbon dioxide is formed, CO2, formed when oxygen accepts electrons from plants and microorganisms. We will see this also a little later, it will be clearer. Redox reactions in the soil are the result of a cycle started by photosynthesis. Today we will talk about things you probably never thought about it as part of the redox systems. That's why I said at the beginning, Not only they are important in the soil environment, but in the environment surrounding the soil. Soil is involved, but it's more than just the soil. So redox reactions in the soil are the result of a cycle started by photosynthesis, which is carried out by plants. Photosynthesis is carried out by plants, but we'll see how that cycle, how it affects the redox reactions in the soil. The soil reactions complete the cycle as they soil react. Remember, we talked about a cycle. That cycle started by photosynthesis. But what's the role of the soil in that? The role of soil in that, the reactions complete the cycle as they utilize the energy stored by photosynthesis. So reactions complete the cycle because they utilize, they take advantage and use the energy which is stored in the plants by photosynthesis. Dispose of organic wastes, the decomposition and the disposal of the organic waste in the soil system. Produce the CO2 needed for additional photosynthesis. Remember, when you talk about the cycle, that means you start somewhere and you end up going back to that point again. So the soil reactions produce the CO2 through the decomposition of organic waste, okay, through the respiration of plants also and microorganisms in the soil. Okay, so they produce the CO2 needed for additional photosynthesis. You remember that CO2 is needed by the plants to carry out the photosynthesis. They take it through the stomata of their leaves to start the photosynthesis process. In photosynthesis, the carbon in CO2 accepts electrons to change from an oxidation state of C4 plus to C0 in carbohydrates, CH2O. This is a simplified form of a carbohydrate molecule, simplified form, so that it just shows the ratio. And that means you multiply it, we have a long chain, but we simplified it in CH2O. So carbon in CO2, remember, oxygen is divalent, so 2 by 2, it gives you 4 negative charges. So carbon is 4 positive charges. So C4 is carbon in CO2. When it becomes part of organic compounds, it has a valence of 0. This is very important to remember. Carbon in carbohydrates and other organic compounds, it has a valence of 0. In CO2, it has a valence of +4. We'll look at photosynthesis. So plants take CO2 from the atmosphere, goes into the plant. This is the reaction written in a chemical way. So it needs electrons, hydrogen ions to give you CH2O, what we just saw, the carbohydrate, plus H2O. This is the simplified form. The oxidative part of the reaction is the loss of electrons by O2 in water to become O0 in O2. Remember, a while ago, I just told you that oxygen, this is the molecular form, oxygen that's in the air, oxygen that you breathe, oxygen that the plant roots take. It's O2 as a gas. It has valence of 0. Okay, if it becomes part of water, it becomes divalent. It carries 2 negative charges. So 2H2O, the oxidative part, remember there are two parts of this photosynthesis, an oxidative part and reduction part or reductive part. So this is the oxidative part, 2H2O. Okay, remember, this is oxygen in water. It becomes O2 with 0 valence, 4 electrons, 4H. Remember, when you balance an equation, a chemical equation, the positive and negative has to be same. So 4 positive charges from hydrogen, 4 negative charges from electrons, it will give you 0. So you have the equal negative and positive. And if you look at all the atoms on the left, has to be the same number as on the right. So it's a balanced equation. 2 times 2, 4 hydrogen here, 4 hydrogen here. 2 times 1, that's 2 oxygen. We have 2 oxygens here. And the charges are the same. Positive, negative to give you 0 charges. Oxygen is the electron donor and carbon the electron acceptor. Remember, if it donates, because here it has 2 negative charges, it donated its electrons and it became a valence 0. So it gave up its electrons, gave it to Wu, of course. And carbon, we will see the electron acceptor in photosynthesis. We will see the other half of it. This is the other half of it from C plus 4, remember, it became C0. Here from 2 negative to 0, the opposite. The above equations each describes only half of the reaction. So they are called half reactions. The oxidative part or half and the reductive half. So if you add them, the equations, chemical equations can be added just like we do mathematical equations. You put them under each other and you add them. If you add this to and this, you end up with the overall reaction of photosynthesis, the sum of the half reactions. So the total reaction is CO2 plus H2O to give you CH2O plus O2. And all of you always know that plants take CO2 from the atmosphere. Of course, it utilizes water to give you the glucose first, but the first organic molecule that's produced. And plants always, when they are going through the photosynthesis, they give oxygen in the air. So that's why people say it's healthy to be around the plants, around trees, and because they produce O2 around them, and they produce O2. Now the other part is the respiration, which happens in the soil. This is inside the soil where the plants respire and use oxygen. We'll see. The other half of the carbon cycle is the oxidation of carbohydrate, respiration, and the many organic compounds synthesized from it. So remember, photosynthesis is the other half of the carbon cycle. We talked about photosynthesis, now we talk about respiration. This is the other half of the carbon cycle, is the oxidation of carbohydrate, which is the respiration, and the many organic compounds synthesized from it. The plants only starts with the first molecule, and they also manufacture so many organic compounds within that plant system. The half reaction of carbohydrate oxidation is, again, this is a simplified carbohydrate plus H2O to give you CO2 plus 4 electrons plus 4 hydrogen. Again, these are all, if you look at this equation, it will be a balanced equation. Look at the atoms or the elements on the right, on the left, they have to be equal. The charges have to be positive, negative, the same. 4 negative, 4 positive to give you 0 charges. In order to in order to obtain this energy and carry out the half reaction, organisms must find an electron acceptor. If oxygen is present, the half reaction of electrons acceptance is O2, of course. O2, remember, 0 valence. When it takes electrons, it becomes an ion in water carrying 2 negative charges. So this is the equation: O2 plus 4 electrons plus 4 hydrogen. It gives you 2 H2O. So electron acceptor in this case is the oxygen, changing from the gaseous 0 valence form to the ion form in water carrying two negative charges. Now we will move to another important thing that teaches us about how easily other things, other metals, ions, things in the soil system, how easy for them to be oxidized or reduced. The tendency of a substance to donate or accept electrons is given by its electrode potential. I don't know, and I hope that you have studied some of that in your chemistry courses, but we will go through a very simplified form of it, not deep, but so that you understand what's going on in the soil system. Okay. The mouse disappears many times, but eventually we find it. Okay. High electrode potentials mean that the elements or ions on the left side of the corresponding equation would readily accept electrons. When you have high electrode potentials, we will see these numbers are high. What does it mean? That the elements or ions on the left side of the corresponding equations, on the left side here, this is the right side, this is the left side, would readily accept electrons. So if you have high electrode potentials, you look at the equation that has that high electrode potential, and you would know that the element or ion or whatever it is, which is on the left, would readily accept electrons. And we know that. So fluorine and chlorine, they are most of the time we find them in the negative ionic form. Chloride, you can hardly ever find it in this form, or fluoride. Most of the time we find them in the negatively charged. So they accept electrons readily. They quickly go into from the zero form to accept electrons to change to the ionic form, negatively charged. And so we say they have high electrode potentials. Halogens, these are halogens, for example, have high electrode potential and thus are strong oxidizing agents. Remember these terms, you should remember what do they mean. Now, these easily accept electrons, so they are quickly reduced. But when something is reduced, it oxidizes whatever it combines with. So they are strong oxidizing agents because they are quickly reduced. They readily accept electrons, which means they go through reduction. If they themselves go through reduction, they oxidize other things, okay? Now, if we have low electrode potentials, this is the opposite of what we have seen, means that the elements or ions on the right side of the equation donate electrons instead. So we'll talk about this sodium, calcium, potassium. They have low, see this earlier we saw positive, high electrode potential. These are low, negative forms of the electrode potentials. So they have low electrode. What does that mean? So we look on the right side, the elements or ions on the right side donate electrons instead. And donate electrons, that means they become positively charged. And also we know in nature, sodium, calcium, potassium, always found in their ionic form. We don't find them in this neutral form. So they are strong electron donors. They give up their electrons and they become positively charged. So they are Na+, Ca2+, potassium+. So they donate electrons to become positively charged. The major electron donors in soil are freshly fallen plant matter and soil organic matter. So what are the major donors and acceptors in soil that we're interested in? The major electron donors. Remember, electron donors, that means they give electrons to become positive. And soils are freshly fallen plant matter and soil organic matter. SOM, you remember we read that and we learned that humus is, is soil organic matter. Okay, the freshly fallen plants are residues, but the humus is the soil organic matter. The role of soil in oxidation reduction reaction is to provide electron acceptors for the oxidation of organic compounds. Organic compounds, the decomposition of the organic compound is actually an oxidation process. When we say that the organic compounds are decomposed in soil, that we use this general term. In reality, in real chemical term and terminology, it's an oxidation process. So the role of soil in oxidation reduction is to provide electron acceptors so that these oxidation take place. The oxidation decomposition of organic matter takes place. If they have to be oxidized, that means you have to provide an electron acceptor which will be reduced. If these are oxidized, you have to have something that's reduced, that accept the electron. Oxygen is the strongest electron acceptor in nature. Oxygen, of course, when we say oxygen here, remember we talk about O2, the gas, the oxygen that's present in nature. And if it accepts electron, it changes from O2 with zero valence to O2 negative. It has two negative charges. It becomes part of compounds, parts of water, parts of organic compounds. Oxygen is also the only electron acceptor that plant roots can utilize. Remember when we said that respiration a while ago, when we looked at respiration, they use oxygen. Plants use oxygen through their roots. It's the only electron acceptor that plant roots can. They cannot use any other. That's why respiration, plants, you need oxygen. They cannot use any other substitute for oxygen for their respiration. It has to be there. And that's why aeration in the soil is extremely important, because if you don't have enough oxygen, if you don't have the availability of oxygen, which is the electron acceptor for the plant roots, then the plant root cannot respire normally and perform all the physiological processes within the plant system. If oxygen is unavailable, soil microorganisms can utilize other electron acceptors. Remember, plant roots cannot. They can utilize only oxygen, but microorganisms can utilize other electron acceptors, not only oxygen. That's the difference between microorganisms and plant roots. What are the other secondary, primary? Remember, primary, the major one is oxygen, but we have also prominent secondary electron acceptor in soils. If oxygen is not there, if there are other ones that can do the job, what are they? We have FeOOH, goethite, if you remember, plus electrons, plus hydrogen to give you Fe2+. We have Mn, it's written O1.75. We'll see why we write that. And again, it becomes Mn2+. So MnO 1.7 signifies, it tells you what it is. It signifies, it means the complex Mn3 and 4 oxide in soil. So you have Mn, manganese in trivalent, and also 4 charges. It can be tri or quadrivalent, okay? Can carry 3 charges, 3+ or 4+. If it becomes 2, that's reduction, okay? So here is also reduction. Iron here is ferric. it became ferrous here from 1.7, which is the average. Because of these averages, so it becomes 1.75 to indicate that this really combination of two types, two valences of manganese. So they take the average of that, but you don't find that average like that, but it's to indicate that you can have two valences of manganese. If you average them out, you will get this. Again, to become Mn2. So these are reduction processes. Okay, where Mn2, we already said that. Now, also, you can have sulfate reduced to sulfide. These are the oxidized forms, the important forms the plants like. When you have aeration, if you have poor aeration, oxygen is not there. That's why these become prominent secondary electron acceptors. They will be acceptors to be reduced from oxidized form to reduced forms. So the nitrate becomes nitrogen gas. Nitrate also can becomes NO2 minus. N2O can becomes N2 gas, and hydrogen can become H2 gas. All of these secondary, we call them secondary, the important secondary electron acceptors when oxygen is not available in enough amount. So these take the place of oxygen. And remember, microorganisms can utilize these, plants cannot do that. Okay, so the prominent secondary, again, what's the importance? What can we say about this situation that we just talked about? In addition to yielding less energy, secondary electron acceptor also yield products unfavorable to agriculture. Most of what you've seen, these are not things as farmers, as good soil people, we want to see them in the soil. If you see these, that means something is wrong, something's not, which means you have lack of aeration, so the soil is not healthy and it's not good. So in addition to yielding less energy, the amount of energy that comes out of it for the plants is not enough, secondary electrons also yield products unfavorable to agriculture. They are not good. We don't want them to be there. The reduced oxidation states are often more toxic than the oxidation states that are stable in the presence of oxygen. So ammonia and nitrite are more toxic than nitrate. Nitrate is the oxidized form, for example, and H2S is more toxic than sulfate. We saw, I'll go back to that slide. You see all these sulfate, sulfide, nitrate, all of these here on this side are the oxidized form. That's what we want them. If you have lack of oxygen, you get these reduced forms. That's what we are talking about. So ammonia and nitrite are more toxic than nitrate, for example, and H2S is more toxic than sulfate. Reduction of nitrate to gaseous N2 and N2O, as we have seen on the previous slide, is agriculturally undesirable because soil nitrogen is lost. If the farmer applies nitrogen in the form of nitrate, where plants can utilize it, if it changes to N2 and to N2 gas and N2, also this is a gas, then you lose them. They go, so that means the farmer lost the fertilizer that he did. So this is the end of this lecture, short lecture